In this final video from Chapter 14, I want to cover a few miscellaneous topics from 14.9 to 14.11, kind of sweeping up the debris at the end of the unit. So, in Chapter 14.9, we'll talk about the effect of structure on acid-base properties. Most of the acids we've looked at, pretty much all of them actually, are molecular compounds, and the question is, how does the molecular structure of the acid influence the relative strength of it as an acid? I want to look at three categories of acids. Hydrohalic acids, as the name implies, these are the acids that are made up of hydrogen plus a halogen, where X is fluorine, chlorine, bromine, or iodine. The oxyacids. Oxyacids are considered one or more hydrogen ions plus a polyatomic anion. And finally, hydrated metal cations, which we've kind of already talked about. So let's begin. Let's look at the four hydrohalic acids and compare the bond energy in the HX molecule to the qualitative strength of that as an acid when it's dissolved in water. HF has a bond energy of 565 kilojoules per mole, and hydrofluoric acid is a weak acid. The hydrogen-chlorine bond has an energy of 427 kilojoules per mole. Hydrochloric acid is strong. The HBr bond energy, 363, a strong acid. The hydrogen-iodine bond energy, 295 kilojoules per mole, also a strong acid. So, what it appears is that there is an approximate inverse relationship between the strength of the HX bond and the strength of the aqueous species as an acid. Now, I got to be honest with you, this really annoys me because I think this is not a really valid comparison. We are talking about two different things, okay? And let's talk about what those two different things are, okay? When we talk about the bond energy, we are talking about HX splitting apart to form a hydrogen atom plus the neutral X atom. On the other hand, when we are talking about the molecule ionizing in solution to form an acidic solution, we are dealing with something entirely different, namely HX aqueous donating a hydrogen ion to water to form the hydronium ion and X minus. So I really don't think it's valid to imply that the bond energy, as shown in the first equation, has anything to do with the ability of HX to donate a proton. Nonetheless, this is what's mentioned in the textbook, so I thought I'd tell you about it. Let's move on. Oxyacids. This makes much more sense. I've drawn here sort of a generic equation for the ionization of an oxyacid, where X represents the central nonmetallic atom in a polyatomic anion. Subscript of M tells how many oxygen atoms are bonded to that central nonmetallic atom. N represents the net negative charge on the polyatomic anion, as well as the number of hydrogen ions that are associated with it when it is neutral. So the questions are, how does the strength of this oxyacid vary with the number of oxygen atoms attached to the central atom in the polyatomic anion, which is M, as well as the identity of the central atom X? So let's consider these two things sequentially. So here are a series of oxyanions, and let's look at their corresponding Ka values. Hypochlorous acid is a very weak acid, 3.5 times 10 to the negative 8. Chlorous acid, HClO2, is a substantially stronger acid, Ka 0.012. Chloric acid, HClO3, has a Ka value close to 1. We haven't really seen that yet. Whereas perchloric acid, we know, has a very large Ka. It is a strong acid. We assume it is fully ionized. So there's a clear trend here, and that is as we increase the number of oxygen atoms on the central atom, the acidity of the oxyacid increases. Okay? That's pretty obvious. So how do we explain that? Well, let's look at the Lewis structures of the first two species in this series. For hypochlorous acid, we see that the OH is bonded to a single chlorine atom, but in chlorous acid, where we add an additional oxygen atom onto the central chlorine, which looks like this, we see that this is a substantially stronger acid by quite a ways. Why would that be? Well, let's consider what's going on in this reaction. Okay? In this reaction, and I'll abbreviate it very simply, the hydrogen atom is leaving as H+, leaving a lone pair on the oxygen to form chlorite anion plus H+. In the second example, the extra oxygen atom, or I should say the oxygen atom attached to the chlorine, remember oxygen is the second most electronegative element on the periodic table, that electronegativity pulls electron density away from the right-hand part of the molecule as I've drawn it here, weakening the OH bond, making it easier for the hydrogen to come off as H+. Another way to think of it is that that additional electronegative oxygen atom on the conjugate base stabilizes the negative charge. So generally speaking, the more oxygen atoms we place on the central atom in the oxy acid, the more strongly electron withdrawing groups we have, weakening the OH bond, making it easier for the hydrogen to come off as H+. Now, let's just consider a single category of acids, HOX, where we vary the central atom X. Hypochlorous acid, where X is chlorine, as we said before, Ka is 3.5 times 10 to the negative 8, and chlorine has an electronegativity of 3.0. Hypobromous acid, in which the central atom is bromine with an electronegativity of 2.8, we see a Ka of 2.0 times 10 to the negative 9. Hypoiodous acid, in which the central atom is iodine with an electronegativity of 2.5, is a weaker acid still with a Ka of only 2.0 times 10 to the negative 11. So the conclusion is that as the electronegativity of the central atom increases, going from bottom to top in this table, the acidity increases. So as X in the middle becomes more electronegative, the acid becomes stronger. So what would our explanation for that be? Well, it's pretty similar to what we had before. If you think about the structure of these acids, so I've got X, O, H, again ionizing to form the conjugate base XO minus plus H plus. The more electronegative X is, once again, the more strongly electron density is withdrawn from the OH bond, weakening the OH bond, and making it easier for the hydrogen to come off as H+, making the acid stronger. That's a pretty clear correlation. For the final category, why are some solutions of metal cations acidic? For example, aqueous aluminum 3+ has a Ka of 1.4 times 10 to the negative 5th. Well, we talked about this earlier in the unit. And what we saw was that if we consider an aluminum cation with 6 water molecules coordinated to it, and a 3+ charge, once again, the whole concept of the electron withdrawing nature of either additional electronegative oxygen atoms or a more electronegative element in the center of the oxy acid, or in this case, the high positive charge of the aluminum cation, by the way, that's 5, not 6, we see that the net effect is to withdraw electron density, in this case from the coordinated water molecule, weakening the OH bond, and making it easier for that hydrogen to come off as H+, making the acid stronger. Let me neaten up my structures here a little bit. That was a little fast. Okay, so we've talked about this before, so let's move on. So, in each of these, we're going to choose the stronger acid from among the pairs and explain the reasoning. HiO3 versus HBrO3. They are identical in their formulas in terms of the same number of oxygen atoms. The only difference is that they vary in terms of the central atom in the oxyanion. We saw that the more electronegative the central atom, the stronger the acid. In this case, bromine being higher on the periodic table is more electronegative, so we would predict that HBrO3, bromic acid, would be the stronger acid because Br is more electronegative, which I'll abbreviate as E-neg, than iodine. H2SO3 versus H2SO4, we saw that the more oxygen atoms attached to the central atom of the oxyanion and the oxy acid, the stronger the acid. And in fact, that's consistent with our knowledge that H2SO4 is a strong acid. So more O atoms on sulfur. In the next example, we compare chlorous acid to hypobromous acid. Now, these are varying in two different ways. Chlorous acid, HClO2, has more oxygen atoms on the central atom, which is making it more a stronger acid. It also has a more electronegative central atom. Chlorine is more electronegative than bromine. So both of these factors make this a stronger acid. So more O atoms on chlorine, and chlorine is more electronegative than bromine. Had those factors gone in the other direction, we couldn't necessarily predict which would be the stronger acid, and I wouldn't ask you that question. The final example, we have two metal cations, 2 plus and 3 plus. Clearly, the hydrated metal cation with a higher positive charge is going to be the stronger acid because it will polarize the water molecule more. So, higher positive charge. Okay, our next category, acid-base properties of oxides. Oxides are essentially binary compounds of oxygen and some other element. Let's list some oxides. Oh, I don't know. Let's see. Sulfur trioxide is an oxide. Sodium oxide is an oxide. Dinitrogen pentoxide is an oxide. And magnesium oxide is an oxide. What are the two major categories? Well, if you look at these, you can see that these four oxides that I've just sort of semi-arbitrarily drawn out of the air fall into two categories. And one would be non-metallic oxides, which would include, among these, sulfur trioxide and dinitrogen pentoxide. And the other would be, obviously, metal oxides, which would include sodium oxide and magnesium oxide. So the question is, what do they do when you put them in water? Well, let's take one example of each of these. If I take, for example, sulfur trioxide, which is a gas, and dissolve it in water, water reacts with sulfur trioxide to form a new molecular compound, the formula of which you can determine simply by adding H2O to SO3. What do you get? You get H2SO4. What is H2SO4? It is sulfuric acid. Let's take another example. If I take sodium oxide and react that with water, well, in this case now, the oxide of sodium oxide is an anion with a 2 negative charge. If OH minus is a strong base, O2 minus is going to be a super strong base. What it will do is essentially remove H plus from water, it will deprotonate the water, the oxide will become hydroxide, leaving behind another hydroxide, and what we effectively have is two formula units of aqueous sodium hydroxide. So we can see two very different outcomes here. Reaction of non-metallic oxides like sulfur trioxide form acidic solutions, whereas reactions of metallic oxides like sodium oxide form basic solutions. And that is our general rule. So, non-metallic oxides react with water to form oxyacids, and therefore we obtain acidic solutions, whereas metallic oxides react with water to form metal hydroxide salts, that is basic solutions. So, let's do some sample problems. Will the following oxides produce acidic or basic solutions when dissolved in water? Write balance equations to justify your responses. Lithium oxide is a metallic oxide. That O behaves as O2 minus, a super strong base. So this will react quantitatively and rapidly with water to form lithium hydroxide, a basic solution. Cl2O3, that's a non-metallic oxide. So I'm predicting that it's going to form an oxyacid and therefore an acidic solution. How do I determine the formula? Well, with these non-metallic oxides, and I honestly don't know what the physical state is, I'm going to take a wild guess and say it's solid. Pretty much all you have to do is mentally add H2O to the formula, and this gives, well, that's going to give me H2Cl2O4, which is not really a thing, but if you divide it by 2, you get 2HClO2 aqueous, which is simply chlorous acid, which we saw before, and this will be an acidic solution. For our final example, we'll take strontium oxide, which as a metallic oxide clearly will form a basic solution. I'll show that reacting with water, and then down here because I've run out of space. Simply aqueous strontium hydroxide, which is basic. Okay, in our final topic in chapter 14, we're going to talk about the Lewis acid-base model. The definition of acids and bases according to the Lewis model is the most general. Not only does it not involve proton transfer, it does not involve aqueous solution whatsoever. According to the Lewis model, an acid is a molecule or ion that accepts an electron pair to form a new covalent bond, whereas a Lewis base is a molecule or ion that donates an electron pair to form a new covalent bond. So I can imagine a generic Lewis acid-base reaction looking something like this. Here is my Lewis base, and here is my Lewis acid. Lewis bases often but not always have negative charges. Lewis acids often but not always have positive charges. What a Lewis base has to have, though, in order to behave as a Lewis base, is a lone pair of electrons, which I will indicate with this blob here with 2 dots in it. The Lewis acid must be electron deficient. It must have an empty lone pair. So in my generic Lewis acid-Lewis base reaction, this is what happens. The base donates a pair of electrons to the acid, and in my product, I have formed a new covalent bond. So what I expect you to be able to do is to look at a balanced chemical equation that represents a Lewis acid-Lewis base reaction, identify the Lewis acid and the Lewis base. Okay? Lots and lots of examples. Because this is the most general reaction, any Bronsted-Lowry acid-base reaction, i.e. any proton transfer reaction, is also a Lewis acid-Lewis base reaction. But here's an example that doesn't involve protons. Okay? If I take the molecule boron trifluoride, which is electron deficient, boron does not obey the octet rule, and react it with the fluoride anion, F minus, okay, the fluoride will donate a pair of electrons to the central boron, which is electron deficient, and in doing so, form the tetrafluoroborate anion, BF4 minus. I'll draw the full Lewis structure here. Hey, Lewis structures for the Lewis acid-base model. Yep, same dead white European male. Actually, dead white American male. Okay, and there's the tetrafluoroborate anion, and I can imagine that this is the new covalent bond that we formed. Okay, so let's do some examples. Oh, but first of all, let's summarize our acid-base models. The Arrhenius model says that an acid is something that produces the hydrogen ion or increases the concentration of hydrogen ion in aqueous solution, whereas a base increases the concentration of hydroxide. The most narrow and specific. Oops, the Bronsted-Lowry, I spelled that completely wrong. The Bronsted-Lowry definition of acids and bases says that an acid is a proton donor, a base is a proton acceptor. In a Bronsted-Lowry acid-base reaction, a proton is donated. And the most general is the Lewis definition. An acid is an electron pair acceptor, a base is an electron pair donor. So, in each of these reactions, we're going to identify the Lewis acid and Lewis base. In the first one, aqueous nickel 2+ cations react with ammonia molecules to form a coordination complex in which the ammonia molecules are now coordinated to the nickel. In order for that to occur, each of the 6 ammonia molecules must donate a lone pair of electrons to the empty coordination sphere of the nickel, forming the nickel-nitrogen bonds. Therefore, nickel is the Lewis acid, and ammonia is the Lewis base. In the second example, water reacts with a cyanide anion to form hydrocyanic acid and hydroxide. Let me draw a little structure here that might make this clear. Okay, all right, these are not separated. So water looks like this. The cyanide anion looks like this. In this reaction, cyanide takes a pair of electrons from carbon and donates it here to form a new hydrogen-carbon bond, leaving behind the hydroxide anion. Since cyanide donated a pair of electrons, it is the Lewis base. I'm going to have a hard time drawing that here. And since water accepted the pair of electrons, it is the Lewis acid. In our final example, I have mercury 2 iodide reacting with iodide anions to form the tetraiodomercuriate anion. Once again, the iodide anions are donating pairs of electrons to the mercury to form new mercury iodine bonds. That makes mercury 2 iodide Lewis acid and iodide Lewis base. And that's all for chapter 14. See you in the next chapter.